So this is lecture 10, and today is the 27th of 2021. All right, hard to believe. Okay, so what I'm going to do today, we will continue with rigid body equilibrium, which is the topic we have been discussing, and we've been trying to solve for unknown forces that hold the structure together or the external reactions forces. We have so far discussed 2D problems. Today, I'm going to get into 3D equilibrium. However, before doing that, since the next topic that we will discuss would be internal forces and starting with frame structures, there's a concept that is very important when it comes to internal force analysis, and that is the concept of identifying what we call or refer to as two force members. I like to first do a problem or two and introduce that concept. Then I will get to introducing the 3D equilibrium. So let's start with that. What is a two force member? Okay. It happens, I'm going to introduce that through an example problem, which I'm not going to solve. There are two problems I'm going to do. One of them just introducing the concept and elaborating on that and do partial solution of the problem. The next problem, I would completely solve that. So because there is a reason for that, because I want to first elaborate through the first problem on this concept. So let's see. Let's say you have a structure that is made of two parts. Of course, you say, I don't care. I'm focusing on finding only the external support forces. Why do I care? The structure is made of different components. I'll show you why. So at this end, the structure is residing on a color system, okay, like this. And let me turn some light on so you can see the page better. It's kind of dark here. Okay. And at this point, let me call this point A. At point, say, B, the structure is supported by a roller. So let me give you also these dimensions. Okay. Let's say this is 6 meters, this is 4 meters. At this point, you have a force of 2.5 kilonewton at an angle of 60 acting on the spin. At point C, now this piece of the structure looks like this. So you have this now, and then you have this pin support here. Okay, so this is your structure, and as usual, and this height is given 3 meters. So this is a typical problem we've seen so far, but look at this. We said the step one is what? You set up step one, you set up X, Y coordinates. And step two is you draw the free body diagram. But look at this problem. You want to find all the external forces, support the action forces that hold this structure in place, right? But if you look at it, if I draw the free body diagram, how many unknown forces do I end up with? There is this color, by the way, makes an angle of 45 degree here. So let's just um, do the free body diagram over the figure to save some time. So if you remove this is the line of motion. So you have one unknown here, R at A, okay? This angle would be 45, this angle would be 45. So that's one unknown. You'll have one unknown here, R at B, this is a roller. And then you have two unknowns, dx and dy, right? Guess what? You have four unknowns and three equations. So this problem, you say, is statically indeterminate. So you cannot solve that, right? That's why this concept of two force members come into play. What is a two force member? Okay, what is a two force member? Let me first explain that concept and then get back to this problem, because we do have a two force member in this problem, which changes the whole scenario of free body diagram. What is a two force member? A two force member is a piece of a structure. Any structure is made of different components, right? So it's a component or a member, okay, that, okay, is this member is attached to rest of the structure only at its two ends. Okay. If you look at this structure is made of two members, this piece and this piece. If you look at this piece, right, it is connected to the rest of the structure, not here, but you also have a support here, support here. But you look at this piece, it is only attached to the structure at its two ends. But not only that, that's one requirement. The other requirement is that both ends are pin supported or are pinned, okay, like this. Third requirement is that no load acts along that member. See, there's no load here. If these three requirements are all satisfied or exist, these three conditions exist, then if you consider the free body diagram of that member, regardless of its shape, in this case, it is looked like this, FCD. I would show you that at this point, you cannot have two unknowns in this direction and in this direction. Rather, you will, or at this end either, you will have only one unknown, and this one unknown are two forces that act along a line connecting the two ends in the opposite direction. They're equal in magnitude and opposite. What I mean by that is this. If you have any member, I did not say what shape it is. These are the only requirements. Let's say you have a member A, B, that is only connected at the two ends to the rest of the structure. These two ends are pin, and no load acts along this member. What I'm saying is, if you connect the two ends, I want to argue that for this to be in equilibrium, you can only have two forces like this that are equal in magnitude and opposite in direction. That is how this member will be in equilibrium. How can I prove that? Let's start with the assumption first that it is not so. That is, okay, for this structure piece to be in equilibrium, I can have a force F1 and let's say F2, okay, F2, okay? And that's how this structure would be in equilibrium. What I will do, I will connect these two ends and then resolve these two forces into their components, okay? So F1y, F1x. I'll do the same thing here. So I have F2x, F2y. Okay? So that's how this structure is in equilibrium, right? But wait a minute. Can I have all these forces? I will prove that you cannot have them. Why? Because if you take summation of moments about A equal to 0, okay, what happens? These two pass through A, this force passed through A, so you only have one force, F2y. So this equation will give you what? F2y times the vertical distance here, let's say D, is 0, and that's it, which means F2y has to be 0. And now if you write summation of forces along y equal to 0, what do you have? You have F1y plus F2y equal to 0. This was already 0. That means F1y has to be 0 as well. So for this member to be in equilibrium, from the last equation of equilibrium, we conclude that F1x has to be equal to F2x, or they are just one force. So what I demonstrated is that for this piece to be in equilibrium, the only way it can be in equilibrium is that you have two forces acting along a line connecting the two ends, and these forces have to be equal in magnitude, opposite in direction. With that said, okay, let me now draw the free body diagram of this structure. What does that mean? That means since this member satisfies all these conditions, it is a two-force member. So I have two choices. I can either draw a free body diagram like this, okay? Okay. Obviously, this one is at that 45 degrees, okay? This force. At this point, I have only one force, and that one force acts along a line connecting these two together. So at D, I have only one force. So now I have only three unknowns and not four unknowns. So this is the correct free body diagram of the structure. Another option is we said that this member is a two-force member. So if I consider the free body diagram of this, it looks like this. So I can just separate this from this rest of the structure, and because that's all that member does, and consider this to be the free body diagram that I am going to consider, okay? Which doesn't make any difference because this is the same as that. So I would consider this free body diagram. Either way, I have three unknowns, same unknowns that you can solve for. Let me show you, for instance, by using this approach. This was point C. If I do that, I resolve these two forces. This forces, this would be RA square root 2 over 2. This is RA square root 2 over 2 because this is 45 degrees. And therefore, I can simply write summation of moments about C is equal to 0. So, and of course, I have this applied load, which I resolved that into its component. This was 60 degrees. So this would be 2.5 times 1/2 cosine of 60. This would be 2.5 times square root 3 over 2 sine of 60. And then I had this applied moment, which was 4 kilonewton meter. Okay, so that's, I have those dimensions here. Oh, I forgot to put that one here. There was also this applied load. These dimensions are given. This was 3 meter, this was 6 meters, and this was 4 meters. Okay. So if I apply summation of moments about point C, I have this moment, which is negative. So I have negative 4 kilonewton meter, which is the applied moment. The reason I took summation of moment about point C was I get rid of these two unknowns. Okay. So I have only this, and of course, this is applied load. So I have negative 4 kilonewton meter. Then you have the moment of this force, which will be also negative. So I have negative 2.5 times 1/2 times this vertical distance, 3. Moment of this force, which about this point, this is a vertical distance, will be positive. So you have plus 2.5 square root 3 over 2 times 6. Then you have moment of this force. This is the vertical distance, would be negative. So you have this RA square root 2 over 2 times this vertical distance, 10. Then you have the moment of this force, which goes this way. This is the vertical distance. So you have plus RA square root 2 over 2 times 3 equal to 0. So this will give you RA. Once you solve that, you find right summation of forces along x equal to 0. That will give you RD. Summation of forces along y equal to 0. That will give you RB. As I said, I'm not going through the solving for numerical values here because I just wanted to introduce this concept. Next problem, I'm going to fully solve that. But any
Professor,
question? Yes.
where did you get the 2.5 from?
Oh, this was given. This was a 2.5 kilonewton.
Ah, okay.
Right. Okay. Any other questions?
When you move the like portion, the kind of curved portion off of point C, why do you only have like how do you have the like just the force pointing left and then
Because
also like the two forces on the ends of the curved portion?
sure. See, what I argued was that this piece, okay, is a two-force member. So for that to be in equilibrium, okay, you can only have these forces. I call them RD and RD. So at the point of connection of these two, right, law of action and reaction. So here you will have a force equal to that and opposite in direction. That's why you have only one unknown here. Did I answer your question?
Yeah, I think so. Thank you.
Sure. Thank you. All right, so let me do another problem, and this time I'm going to actually uh, show you the complete solution, okay? All right, so this is another problem. And as I said, the main reason we are introducing this concept is not now, is the next topic when we get into frames. But I wanted to show you because this concept is important in 2D, and that's when we will be talking about frames. So let's say you have a structure like this, okay? You have an applied load of 800 Newton here, an applied moment of 900 Newton meter. This distance is 2 meters. This distance is also 2 meters, but right in the middle, that is right at 1 meter and 1 meter here, you have another load of 600 Newton, okay? And this is a problem, and this distance is also given, 1.5 meter. So the problem states is find all unknown support reaction forces. Okay? So you look at this problem and you see you have a pin here, you have a pin here, right? So you have two unknowns, two unknowns. No way you can solve the problem because it's statically indeterminate. However, if you pay close attention to this problem, this is how you're going to solve that. You set up as usual your x, y, but when it comes to the free body diagram, you will pause and you see that, wait a minute, true that this represents a support which is pin and supposedly with two unknowns, but this is a two-force member. That means if this piece going to be in equilibrium, you have to have only one force acting in this direction and this direction. So let me call this F of B and F of C. FB, of course, is equal to FC. So this support represents only one unknown. So when it comes to your free body diagram, you have two options. One is this, okay? This is the problem. This is the beam you have, okay? So you draw a line connecting these two. So you have only one unknown here at RC. And this slope is given because this is 1.5 meter. This is 2 meters. So in a way, this is 4 and 3, 5 slope, okay? Then what else you have? You have your applied loads, 900 Newton meter moment, 800 Newton force. Here you had 600 Newton. And then here is obviously a pin. So you have two unknowns, AX and AY. So this is your free body diagram, which consists of only three unknowns. Another option is, of course, that you can, knowing that this is a two-force member, you can look at the free body diagram this way, that at this point B, this structure is supported by this member, and that B represents only one force here. These are the other two unknowns, AX, AY, and these are the applied loads. Both free body diagram 1 and free body diagram two are the same as far as when it comes to equilibrium. So you can use either one, get the same answer. Since we are used to this, I'm going to consider this free body diagram. I'm not going to cut the structure apart. We'll see that later when we introduce the concept of frames. So if I start with that, I can simply take summation of moments about point A is equal to 0, because that is a point. And of course, I need to resolve this force also into its components. This would be 3/5 of RC. This is 4/5 RC. Okay. When I break this into its components. Okay. So if I take summation of moments about A, these two unknowns and the component of RC here will go through A. So I only have this force generates a positive moment. I have 4/5 RC times the vertical distance, 1.5. Then there's no other unknown. You have these two forces, both generate a negative moment about this point, and this moment is already applied a negative, so that is negative 800, I'm sorry, negative 900 Newton meter. Moment of this one would be 600 times the vertical distance, so you have negative 600 times this distance, which is 1 meter. This is 1 meter. This is 2 meters. So this is times 1. This one at a distance of 4. So you have negative 800 times 4 equal to 0. So that's summation of moment about A. If you solve for RC from this equation, you get 3,920 Newton, which is acting in that direction and comes out to be positive. All right. So now you write summation of forces along X is equal to 0. And that will give you AX plus 4/5 of RC, which is 3,920 equal to 0. So that tells me AX would be a negative value of 3,130 Newton. So came out to be negative. That means my assumed direction for AX was wrong. So I would correct that. It should be in this direction. Therefore, this would be negative and this is positive. So AX is acting in this direction. We write summation of moment forces along Y is equal to 0. What do I have here? I have this force, this force, this force, and this force. So I have 3/5 of RC, which is 3,920, plus the unknown AY minus 600 minus 800 is equal to 0. And you see that AY comes out to be negative 950 Newton, which means the assumed direction for AY was also wrong. So AY is actually acting downward. So this is negative, this is positive. So this is AY. Okay. Any questions?
I have a question.
Please.
So in the free body diagram, what is the difference between the 800 Newton force and the 900 Newton meter force?
Oh, this is not a Newton force. This is 900 Newton meter moment. This is an applied moment, like a couple. It's a
Okay.
free moment that you put it here. So if you have a moment which is applied, it only comes into picture, right, when you're writing summation of moments, which is in this
Oh,
equation.
okay.
But when you're writing summation of forces, that is not a force. That's an applied moment, so you don't see that.
And you can
Yeah.
technically put the applied moment anywhere, right?
Absolutely.
Okay.
Yes. This applied moment, they show it on the diagram that is applied there, but we remember from couples, they are free moments. You can put it anywhere you want because they only play a role in summation of moments, right? So when you have an applied moment, who cares where it is applied, right? Force makes a difference because the moment of a force is a force times the vertical distance. But an applied moment is already, that distance is already included that has given you the moment. Yes. Any other questions? If not, as I promised, let me now introduce this topic, okay? Which is, I mean, the extension of what we have been doing, and that is 3D equilibrium. So that's what I'm going to now introduce. 3D equilibrium. So the concept is the same, or the objective is the same. You have a three-dimensional object supported, and we want to find the unknown forces that are holding this structure at its supports. So how do we do that? Okay. In 2D, it was easy, right? In 2D, we said that the kind of supports that hold a structure in place are restricted to these three types. Okay. This represented one force perpendicular to the potential direction of motion. This represented two forces, potential direction of motion, and this represented three unknowns. Okay. In 3D, the way objects are held in place, supports are more complex. And for that reason, you are not expected to know exactly what the function of those supports are because you're either given enough information that you can find out, figure out what those unknowns are, or you're basically given what the unknowns are and in what direction. But these are typical types of 3D support mechanisms that are tabulated in a table on somewhere in your book. In this book is on the front page, first page, once you open the cover. For instance, you may have just a leg of your chair or a ladder sitting on the floor. Floor is frictionless, so this leg can move in any direction except vertical direction. You can rotate it in any direction. That is, there is no moment resisting the motion, and you can move it in this direction, that direction. The only direction that you cannot move is pushing it into the floor. So that represents only one unknown. If you have a roller or a wheel that is sliding on a rail, okay, what happens? Again, you can rotate it any direction you want. However, you cannot move it in this direction or in this direction. So that represents two. If you have a ball and socket joint, you know what is a ball and socket joint? Think of the hip joint in your body. You can rotate it in any direction you want, right? But you cannot, fortunately, pull it in any of these directions you want. So that represents your hip, represents a support that is resisting the translational motion in three directions, and so on and so forth. As I said, you don't have to memorize these, as was the case in 2D, because you will be given enough information to identify those. So, what is the difference between the 2D and 3D case? As far as the objective goes, is the same, is find, support, reaction, forces. Okay. So step one was what? Set up X and Y coordinates. The only difference in this case is always X, Y, Z coordinates are given. Because in order to describe the geometry of the object, you have to demonstrate it in a three-dimensional coordinate system. So this is given. Step two is when you draw the free body diagram, similar to 2D. So this is, again, 75% of the problem. But now, when it comes to step three, that's where the deviation from 2D happens. And what is that? And that is, in 3D, you have 6 equations: summation of forces along X, summation of forces along Y, summation of forces along Z is equal to 0, and then summation of the moments of all forces is 0. This summation of moments, you can take it either about a point or about an axis. Both of these results in 3 more equations. Okay? The only difference between these two is if you have a 3D object and you have forces acting on this object in such a way that you can find a line that intersects with some of these unknown support forces, if you take summation of moments about that axis, you can get rid of these unknowns. So summation of moment about an axis is analogous to summation of moments about the point in 2D, where you find the point of intersection of two unknowns, take the summation of moment about that point, you get rid of those two unknowns, you end up with one unknown. In 3D, if you find an axis that it intersects with as many unknowns as possible, you start with that equation, you may end up with only one equation, one unknown, like 2D. But you don't have to, okay? You can just use the approach by taking summation of moments of all those unknown forces about a point, but you end up with 3 equations, 3 unknowns instead of 1 equation, 1 unknown first. Okay, I'm going to demonstrate this concept, okay, through an example problem. I would warn you, however, that when it comes to 3D problems, solution just takes a long time. So maybe during 1 hour of class, I can only do one problem. And even not that, I may only be able to solve half of it. So for that reason, the problem that I'm going to do here, which is actually a good problem from your book, 108, I will set it up, try to demonstrate the steps involved to the extent I can. But however, what I have done, I have prepared a detailed solution to that problem that I'm going to send it to you. So we can go through it step by step. And it's a very detailed way I have articulated all the concepts and the approach. So, what is this problem? This is a problem. It is this. You have a basically a ball and rocket support here, support system, which is basically like a three-dimensional hinge, allows rotation in any direction, but prevents translational motion. So if this is X, this is Z, this is Y axis, okay? Length of this or the height of this is given at 12 meter. At a point which is uh, uh, 4 meters from top, I have two cables, okay, that are attached to this point B and are connected to these 2 points on the ground at point F and E, okay, and the location of these are given. It happens that these are along the same line, parallel to z-axis, and the distance from the z-axis is given as 7.5 meter, and the distance of each from the x-axis is the same, and it is 6 meter. So these two cables are attached to the ground, holding the object, but in order to make this stable, okay, we also at point C, which is on top, and in this plane, along a line that is parallel to x-axis, we have also attached another cable to point D. So if you look at this, first of all, step one, as you can see, X, Y, Z is given, as I promised. So it comes to free body diagram, okay? How do I draw the free body diagram? At this point, I have a pin that allows rotation in 3 directions, okay? So I will, to save time, I'm going to actually write show the unknown forces on this diagram using just a different color. So A represents 3 unknowns, and typically, like the 2D, I would assume an arbitrary direction for these unknowns that if I find later on by solving for them, they came out to be negative, that means my assumed directions are wrong. This is also supported at point B with these two forces. So these two also represent 2 unknowns, F of B, F, and F of B, E. Okay. What else? I also have another cable, F, C, D. So how many unknowns I have? 1, 2, 3, 4, 5, 6. How many equations? 6. So I can solve for all of these. But the book or this problem wants to make your life easier. So for no reason, the magnitude of the force in this cable is given 14 kilonewton. So you only have 5 unknowns to worry about. Okay. So what is the next step? I write all the equations of equilibrium, right? These are the tools that I have. And also summation of moment. What I said, I can take summation of moments about either a point, for instance, about point A, where it allows me to get rid of these three unknowns. I only have two unknowns. Or I can take summation of moments about an axis if I can find an axis that allows me to get rid of all the unknowns except one. And I see that, ironically, it is quite interesting. I can see, if I look close, I can see, in fact, such point, such axis. If I take summation of moments about this axis, this force intersect with that axis. These three do. The only unknown I have that does not intersect is only this force. This is known. So if I use this summation of moments about AF equal to 0, this gives me one equation, one unknown. If I use this one, I got rid of three unknowns. So this will give me two equations and two unknowns. Okay? Either approach is perfectly fine. So now, how do I proceed with solving it? Well, obviously, the first step is you set up the vector equation for all the unknown or known forces you have. In 2D, you are only dealing with quantities or magnitude of those because, the moments are just that magnitude times the vertical distance. In 3D, equilibrium is a vector equation equilibrium. So you need to set up all the vector equation for the forces, and then you proceed accordingly by starting this. What I have done, as I said, since there is no time to go through this step by step, I have set up the solution in a step by step. And in each step, I have fully explained what is done. And I have first demonstrated solving the problem using summation of moments about this axis AF, which you remember, to write the summation of moments about an axis, you need to find first moment of all those forces about a point about that axis, right? And then find the dot product of those moments and the unit vector of that axis. So I've set that up in details, and then I perform the operation or the procedure, and then show you how you can find all these unknowns, okay, using that approach, or, and then all of them, or if you want to use an alternative approach, you can use, or you can start with summation of moments about A is equal to 0 first, which gives you two equations and leads to two unknowns. Okay, so you'll get the solution from me, and on Friday I have selected another problem, and since we have the whole hour, I will go through that step by step and solve that problem also. Okay, any questions? If not, I'm going to stop here. So some of you are going to join me during my office hours, some won't. So I will see you at either 11:30 or I'll see you on Friday. Have a great day.
Thank you.
Thank you.
I have a quick question.
Please.
So for the moment about the axis in red, you said there was one unknown. Which unknown is that again?
That is, you see, this one, and this one. and this force all intersect. But how about the FBE?
Right.
It's not
Okay.
intersecting. So that's the only unknown. This one is
Gotcha.
given, so that's not an unknown. So you only have one unknown and one equation. And as you see in my solution, you can easily solve for that one unknown.
Okay. And then the two unknowns about A would be,
Oh, later you use the other equations that you have, summation of forces along
okay.
X, Y, and Z, and you solve for the other unknowns.
Okay, sounds good. Thank you for clarifying
Sure,
that.
thank you.
And it's not like helpful to use the axis that all of them go through, right? To solve the moment, because you want to have at least one unknown to solve for something. Because
You
couldn't you
mean
just
find
use A, B? But that would do
excellent,
nothing.
excellent question. However, if you use this, that's a very good point. But if you use AB, AB intersects with every single force.
Yeah.
Right? So there is no moment because moment of all these forces, right? About this axis is zero, right?
Yeah.
If they all intersect with that axis, you don't have any unknown left, right?
Hmm.
You know what I mean?
So you would only have the like force equations to work with, and you kind of want more information than that. So
Correct.
that's why you don't use it.
Yes, that's right.
Okay. Okay. Thank you.
Exactly. Sure. And before I forget, I'm going to send you this solution.
Hi, Professor.
Hello.
I had a really quick question. So I got my midterm one back yesterday, and I realized I should have talked to you about this at the beginning of the semester, but I am registered at the DRC and I
Great.
use the extra time accommodation. However, even with the accommodations that I've had since I started college, it still doesn't really fully help my test anxiety. So my midterm didn't really reflect my knowledge of the course. So I was wondering if you did test corrections or anything like that,
I
or is
will
there?
be, I'm so glad. I am so glad that you told me that. I will be more than happy to go over that and give you the extra points or consider that. And also, if you kindly remind me next time, I will give you another extra 30 minutes.
Oh, I thank you so much. Yeah, it's just the test environment. I don't even know what it is.
I
Just
can
everything
fully
leaves my brain.
Absolutely. I can fully understand it's not your fault.
Mhm,
So I can fully understand that. So next time, please warn me ahead of time. I'll give you that extra time. Or
mhm.
actually, I will give you how best that would help you. I will give you an open-ended.
Oh, I thank you so much, Professor. The time that I had on this exam actually fit pretty well. It's just the overall
I understand.
everything. Yes.
Don't worry
Thank you
about
so much though. So in terms of test corrections, when do you want me to have them by, or like set up a meeting,
it. What
or
I
what
would
would
do this. No, 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 you don't have to. I will put a mark next to your exam, which I will definitely correct that, give you more points. But even to make it more meaningful or help you when you do your next exam, I will look at it and even accordingly, I will raise your points to represent your knowledge.
Thank you so much.
Oh, my pleasure.
Because if afterwards, if you want me to like submit it as, because it was funny, I was looking at what I submitted and I saw my grade, and then I looked at the problem. I was like, why did I do that? I know how to do it this way, and it was just.
Yeah, if needed, to be honest, I don't mind if you send me the solution that you could have done, let's put it this way, uh, uh, if you had more time. And I would consider that as the grade for your exam. That's another
Okay,
option.
if you don't mind, I would love to do that option just
Absolutely.
to show what I
I
know.
don't mind at all. But just email it to me. In
Okay.
fact, that may be a good idea because if once you email it to me, I use that to change your grade. That's a better approach. Sure. Thank you for sharing that with me.
Thank you so much, Professor.
My pleasure.
Have a great day.
Have a good one. Sure.